Okay, so we're back. Let's see. So let me start by restating just the first pictures and then I'll do the math. We have a distribution. Okay, we can call this distribution the A distribution. And we have another distribution, which is the B distribution, let's say. Okay, now we have some data. Let's say that, let's see how I did the math here. No, actually instead of A and B I called it 0 and 1, which makes more sense. So let's say this is the 0 distribution and this is the 1 distribution, and then we have some set of data. X was measured and we had x1 and x2 and x3 and x4, etc. right? Well, actually let's not say etc. Let's say that the last one was xn. Now if we calculate the likelihood of this data in the distribution 0, the likelihood of the data here in the distribution 0 is the product of all the probability distributions. Let's say I'm calling them J0 from J equals 1 to n, right? So the likelihood is the product of the PDFs, right? So, I mean of the PDF entries. So we come here with our data in the 0, read, all those other PDFs, we multiply them together, that's the likelihood of that data in L0, right? Now, if we do the same thing here, we get that the likelihood 1 is of course the product of all the data of probability J's measured on the probability distribution number 1. And we have that. Now, we define delta capital at n as the log of the ratio. So let's say we take the likelihood of the first probability, which is, or the number 1, not the first, and the likelihood of the second one, which is this way, right? So this is the log of the likelihoods, of the likelihood ratio, I'm sorry. This is the likelihood ratio and we're taking the log. And I'm defining that as capital delta N. Now, before doing any math, if the data is coming from the distribution 0, let's assume to start with that the data x1, x2, x3 is actually coming from 0. Then its likelihood in 0 should be larger than in 1, right? Okay, that means that this denominator is bigger than this numerator, right? Okay, if the denominator is bigger than the numerator, this ratio, the likelihood ratio, is less than 1. Therefore, the log of this ratio, which is less than 1, is negative. So we expect this lambda to be negative if the distribution, if the data is coming from the distribution 0. Alternatively, if the data was coming from distribution 1, or was closer to coming from distribution 1, then we expect the likelihood of distribution 1 to be bigger than the likelihood of distribution 0 for that data. This number would be greater than unity, and the log would be a positive number. So, from that perspective, we can see that at time station n, notice that we're not making a decision here as to what's happening at any given sampling time. We're making a decision, or attempting to make a decision, on the basis of what has been measured all the way from 1 to n. Okay? I forgot to mention this, but now I do it at this point. The format that I'm looking at here is what we would call as change detection instead of point in time detection. previous lectures, we would try to specify whether there was damage or not from the measurements that we made on Monday. So we obtain a model and then we make a certain set of measurements on a given day and we make a decision whether it was damaged or not. Here, we are not actually doing the same thing. What we're saying is we have a set of recordings, N, and we're going to try to see if we make a decision now based on everything that we have recorded in the past from 1 to N, right? So, okay, it'll become more obvious when I do the example. But anyway, so we have the likelihood here for the distribution 0 for that data, the likelihood here, the ratio of the likelihoods, and we take the log. So now all we have to do is a little bit of math here, because you know that the log over ratio is going to be what? The log of the numerator, that is the log of the product. I'm not going to put from 1 to n, but you know that all of these are from j equals 1 to n, right? So it's the log of the product of the numerator, not divided, minus. Is the log of the numerator minus the log of the denominator, right? Which is the product of the probability distributions measured on the 0 PDF. Now, we continue with our simple math here. We take a look at the first term. So the log of a product of probabilities, or actually of the product of numbers, is equal to the sum of the logs. Therefore, we have the sum from j equals 1 to n of the probability j in the distribution 1, right? Minus the sum from j 1 to n of the probability j measured in the 0 one, right? Now, for clarity, at least for me it serves, instead of leaving these things, let me look at a case of 3 numbers so I can make my point easier. So this first sum here would be P1 in the 1. What did I do here? Did I do this right? No, I forgot the logs. So I'm correct up to here. Now I'm saying the log of the product is the sum of the logs of the terms. So I have to say the sum of the logs of Pj1 and the sum of the logs of Pj0. Now we're correct, right? Log of a product, sum of the logs. Now, looking at an example to avoid errors, or to make it cleaner for me at least, I'm going to assume that the sum is from 1 to 3. So this would be the log of P1 in the 1 plus the log of P2 in the 1 plus the log of P3 in the 1, right? Minus the same thing in the 0, right? With the parentheses here. So this would be the log of the P1 in the 0 plus the log of the P2 in the 0 plus the log of the P3 in the 0, etc., right? Therefore, we can see that lambda n, this is just, I used 3, but of course it's n, right? So you can see that I can pair them like this, right? So this is log of the probability 1 in the 1 minus log of the probability 1 in the 0. So this is the subtraction of 2 probabilities. So this is the log of the probability 1 in the 1 divided by the probability 1 in the 0, right? The same thing with the 2 plus the log of the probability 2 in the 1 divided by the probability 2 in the 0 plus like that, right? So you can see that if I have n, I get to the formula okay, after n of them, we get the formula that lambda n is equal to the summation, right, of the logs of the ratio of the probabilities j in the first distribution divided by the probability j in the zero distribution. I mean in the 1 and in the 0, from j equals 1 to n. So this is our formula. So this formula is telling us what we started with, which is, actually if I raise the formula I can get back to the very beginning. So apart from this derivation, which you already have, what is important is to say that what this is, lambda n, is equal to the log of the ratio of the likelihood of the data in 1 divided by the likelihood of the data in 0. Okay. It's the log of the likelihood of the data in 1 divided by the likelihood of the data in 0. Log of that ratio. And when we do the math, we see that we can calculate it as simply the sum of the logs of each one, right? Probability distribution j in 1 or probability distribution in j 0. So what happens then in this approach is the following. We plot on the vertical axis the value of lambda n. And on the horizontal axis, the test. So this is n here, right? 1, 2, 3, 4, 5, etc. 6, 7, 8, 9. Now, let's assume that this is n is time, right? Because time is passing as we're doing the test. Imagine that at this time is when damage began. So, and let's assume that the probability 0, PDF 0, is what we think it's reasonable for undamaged. And PDF 1 is more likely true if it's damaged. So when we start at the beginning, the system is undamaged over here, right? And because the system is undamaged, the probabilities Pj are the bigger ones. This ratio is less than 1, these logs are negative, and this thing tends to be negative. And so what we end up finding is that this thing starts drift. Let's say we put it at 0, we get a negative number, right? Now in reality, of course, this is a random process, so sometimes it goes up and then it goes down, but basically you see some sort of a trend of this thing decreasing, right? Because you're undamaged and your denominators are generally larger than your numerators in your probability likelihood ratio test, right? So you have that. As soon as you get beyond this point, this now is the opposite, right, in the sum, and so you tend to detect that this thing starts doing this, right? And so the point is that in this approach we detect damage as simply the shift from having a negative slope to having a positive slope, right? And where that change tends to take place is the region where the damage appeared in the structure. Now there are many ways to do it, because of course this thing will always, how should I say, it's a random process, so this thing could be going down and then it could be going up. So you don't want to be fooled necessarily because, you know, probability was going down like this and then it went up a little and then you're going to say right there it was. No, because, you know, it might be coming down again. So there has to be some sort of clear trend that you see something like this, right? So there are various ways to apply this approach. One of them, that is perhaps one of the most popular, is that when you do the computation, let's say, let me explain it in a very noisy case. You start here, you expect negative, but it might actually start going up for a few steps. And then it goes like this, and then it went down, right? Now, in some applications, what people will do and recommend is, okay, it turned down, then you reinitialize it and start at 0 again. And then here it goes down again, so you reinitialize it. It goes down again, you reinitialize it. Now it goes up, and then it went back down, you reinitialize it. So anytime you cross to the negative side, you just go back to 0 and start again with the data as you go. And then in this case, at some point, this thing starts going up and doesn't come back down, right? And it does this. Then what people will do is to put a threshold H, let's say, H plus, and say, I tell my automated system that when the level H cross gets crossed, then I announce damage. And there's various ways to select that H plus. I'm not going to discuss them right now. So this is a common approach to do it. Just reinitialize when it goes to 0 and then reinitialize, and then when it starts going up, you have a threshold cut and that's it. Now what I do want to do in the remainder of the time on this part is to discuss from a theoretical point of view, what are these two distributions in damage detection? What are reasonable ones? Right? Because we said there is a distribution 0 and there is a distribution 1. So what is a reasonable PDF 0? Now, again, if we had so much data from the reference state before the system, when the system we are sure is undamaged, we got a ton of data. We can certainly take that ton of data and do a statistical analysis and come up with a distribution that is the one that best fits the data somehow, right? So we could establish that distribution from data in a very heavy, data intensive way. Or, much more likely, we just have some data, not a ton of data, but we have some data, right? We have some data from the reference state, and let's say in that case, now let's go to structural health monitoring. Let's say that that data is that we've been doing system identification and we find the frequency of the first mode, the frequency of the second mode, and the frequency of the third mode. So actually I shouldn't call it W. So our vector X is actually 3 numbers. And what we have for data is F1, F2, and F3. And we do that experiment over a number of days, right? Hopefully under environmental conditions that are not so different. And so this is our data matrix, right? These are the number of samples that we obtained in the reference state. So we know the system is not damaged at this time, or we make the assumption that the system is not damaged at this time. We have from prior experience, we know that it is not unreasonable to assume that this data that we have for our frequencies is reasonably Gaussian. So we postulate that the distribution of this data is multivariate Gaussian. We assume. If we're going to assume that our data is multivariate Gaussian, then what? Then we know that what we're saying is that the PDF of our data, right, is describable as a constant times e to the minus 0.5 times the Mahalanobis distance, which depends on the vector x, where the constant alpha is equal to 1 divided by the square root of 2 pi raised to the k, right? In our case, k was 3, multiplied times what? Times the determinant of our covariance matrix. So we have to find the covariance, right? Now to find the covariance, I discussed it before, but I'll do it again. We have our data matrix, right? It has 3 rows in this case. So now we have the mean. So this is this is the mean of F1, this is the mean of F2, and this is the mean of F3. So the average of that row, this row, and this row. We have 3 means, right? That's the mean. Now we have our data centered. How do we center the data? We simply subtract the mean from each entry. So this becomes F1 minus F1 bar, F2 minus F2 bar, F3 minus F3 bar, and that's for the next, and for the next, and for the next, and for the next, right? And we now have our data centered to the mean. Now that we have our data centered to the mean, then we say, let's see, x, right, centered, times x centered transpose, that is this long thing, multiplied times this thing like that, gives us a matrix which is 3 by 3, right? In our particular example. That matrix, that is 3 by 3, if I divide it by the number of samples, let's say the number of samples is capital N, then 1 over N multiplied times XC transpose is the covariance estimate, empirical estimate, okay? Of course, this is an empirical estimation because this is what you got from this data this time, right? If you had done the data again for the next n samples and you did the calculation, the number would not be exactly the same. But if you have enough data, then this covariance should be stabilizing to something quite reasonably constant, right? Representing the actual true covariance that we will never know. So, okay, so now what is the Mahalanobis distance? The Mahalanobis distance, which is the exponent here in the PDF, I'll erase here. Right? So we have our covariance, we can calculate our alpha, and the Mahalanobis distance, which depends on the vector that we measure, is simply the vector that we measure minus the mean multiplied times the inverse of the covariance times the transpose times the vector that we measure times minus the mean again. So this is a scalar, right? So this is a scalar. So even though we had 3 frequencies, when we look at this number that goes into the probability distribution of these vectors, we have a scalar called the Mahalanobis distance that is like this. Now, in the previous class, and I repeat now, the Mahalanobis distance follows a chi-square distribution with k degrees of freedom. In this case, k is equal to 3, right? In this made-up example. So the chi-square distribution is just a distribution that is followed by the square of values that come from a Gaussian and who have unit variance, right? The fact that this is with an inverse here normalizes this to unit variance. So now the beauty of this, notice again, I said it last time but I'll say it again, is that even though here we had 3, right, and we were talking about a multi-dimensional probability distribution here, by the fact that we have shifted our focus from the PDF of the actual data to the PDF of the Mahalanobis distance, that's chi-squared, that's scalar, that's something that we just draw. There's only one variable, right? The one variable, even though we have a vector here, once we put it into this formula, we get a number. Now, when we were doing novelty detection in the previous class, our idea was simply to compute whether the Mahalanobis distance that we get in the damaged state for any, well, okay, let me repeat it just in case, just to set where we're going. Because I know this stuff can be quite confusing. So before, okay, we went like this. We said we have the data matrix. From here we have a mean vector and we have a covariance. All right? Then we say, and we know that there is k degrees of freedom, right? Then we say, we look at the chi-square distribution with k degrees of freedom, and that chi-square distribution with k degrees of freedom may look like this. And this vector, this variable here is z, where this z is our data minus the mean transpose times the covariance to the -1 times the area minus this thing like that, right? So we have any vector that we collect, we calculate its z. And then what we simply say is, if the z is bigger than some if the z is bigger than some value, z critical, then we say that that's very unlikely because there's very little probability left. And so we say that damage occurs, or damage is announced, if z is greater than zz, right? And we find zz using the inverse zdf, right? So we said zz, we found it with, let me see if I remember, something like chi squared, is it chi? Chi squared, no, I can't remember the command. It's inverse CDF. Let's see if this is on. Yeah, chi squared inverse. So is chi squared inverse, right? So we find that ZZ to be the chi-squared inverse, where this here would be 1 minus the type 1 error, and then here is the number of degrees of freedom. Okay? So this would have been 0.95, for example, in case we wanted 5% error, 3, and we get the ZZ. Damage then is announced if Z, for any data that we get, is greater than ZZ. Okay? There's one thing that I believe I wasn't clear, and that's this. The data that we have here, which we use to get the mean and the covariance, is data that we obtain while the structure is in the reference state, right? The structure is not damaged at that time. We have to be sure that we are operating with data from the reference condition. So, to put a timeline, if time is running this way, for a certain amount of time, okay, this is, if you want, you can call it training, okay? So during that time is when we obtain this data. And it is from this data on this time that we obtain the mean of the vector that we're looking at, the covariance of the vector that we're looking at. Now, in many applications, there could be something called a, after training, there could be another period here of calibration before we begin, but I'm going to skip that right now. I'm just going to say now we are testing. So now we are testing means that we have this mean, we have this covariance. This day, you know, Monday of, you know, 3/3/2025, someday, right? We come this day and we get a vector xi with 3 numbers. What we want to determine is this okay? So what do? We take this vector x that we got that day, we subtract the mean, but what mean? The mean of this data, right? That we obtained during the training time. And we transpose it. And we multiply it times what? Times the inverse of what? Of this covariance, which was computed from the data of the reference state, right? And then it gets multiplied times itself again. And this gives me one number, right? Z. All right? I've already established at this time, using this data, that there was a Z critical. And that was based on a chi-square distribution, as I explained before. Now, at this point, I just compare Z with ZZ, right? So notice, because this can be confusing sometimes, this is training data, this is the data used to get the mean and the covariance, that should get stored. Once you start testing, you pull these vectors out, these vectors are subtracted times this mean, normalized times this covariance to obtain the Z that is then compared to this Z. Okay? That is what we did in the previous class. Now, we want to do a little more. Okay, so we do have, again, just like before, we have some data, we have some x bar, we have some tau, we know how many degrees of freedom there are. And from that we say that the Mahalanobis distance of that data is chi-squared with k degrees of freedom. Right? That's true. Now, the question is, what happens after damage? After damage, see, in the novelty detection method, that I just finished restating, we say nothing with regards to what is going on after the structure gets damaged. We just ask the question, does this look like it was coming from the old distribution? Yes or no? We don't know anything about the damaged one. Now we're going to try to say something about the damaged one, even though we don't know the damage. But what we're going to say is this. In the undamaged state, we had this mean, undamaged, and we had a certain covariance. What we're going to say is that the damage produces a shift in the mean. So the mean now becomes the mean damage. And we also make the assumption that the damage does not change our covariance. So this is the key assumption that we're made, right? That the damage is going to shift our mean from the undamaged mean to something else, which is called the damaged mean, but it will not change our covariance. Now, if we calculate the Mahalanobis distance of this distribution, right? Because this distribution has a PDF, which is equal to alpha multiplied times e to the minus 0.5, right? And it should be what? It should be x minus what? Minus its own mean, right? But I'm not interested on computing this minus its own mean because I don't know the mean of this distribution. What I'm interested in is what happens if I subtract the mean of the old distribution. And so we look at this situation, right? What if I look at that? Well, it turns out that this variable, which is xi minus the old mean, is no longer zero mean because the real mean is this one, right? This is a distribution that has a non-zero value because xi minus xu does not have an expected value of 0. And what we find then is that this term, let me call it Mahalanobis bar, is what we call chi-squared non-central. I don't know how to write it in short. But the chi-squared distribution that we are using before when we're using novelty is the chi-squared central. And this is the chi-squared non-central. So non-central means that it is the sum of the squares of a Gaussian distribution that has not been shifted to zero mean, has been shifted to something else. Okay? So, okay. So let's see. How do I say? So let's say that this is the mean x damage minus the mean x undamaged. That would give me three numbers, right? Let's call it U1, U2, and U3. Remember, I don't know this means, right? But I know they're different. So this ratio, I mean not this ratio, this subtraction here, right, is something that gives some value. We define the parameter lambda as the summation of the u's from I1 to k of ui squared. This is called the non-centrality parameter. So the non-centrality parameter is simply the sum of the squares of the difference in the means. We don't know the non-centrality parameter, but we know it's not zero. In fact, if we look at a zero non-centrality, then we're just back to the normal chi-square distribution, right? The normal chi-square distribution is a chi-square with the non-centrality is 0. As soon as the data is not coming from a Gaussian with 0 mean, then we get a non-central chi-squared, and the non-centrality parameter is this. Okay, that almost puts me there now. So what we will say then is, with that introduction, and this will not be clear until you actually try it in some homework and think about it on your own, but I do my best here to lay it out for you first time. So what we will do is this. You have the data during this time, which is the reference. We assume that we have a chi-squared with non-centrality equal to 0, which is a standard chi-squared. Okay? Then, so this is our distribution 0 in the previous discussions. Then here there may be some damage. When we do the testing, we assume that we have a chi-squared with a non-centrality parameter that is not 0, which we will have to assume or take a value. This will be our distribution 1. So what we test when we get data we calculate lambda n, right? Capital lambda n, which is our summation from I1 to n, as discussed before, of the log of the ratio of the probability j from distribution 1 divided by the probability j on distribution 0. So when we're talking about the distribution 0, we're talking about this one. When we're talking about the distribution 1, we're talking about this one. And we must assume some lambda, some non-centrality. Okay? Now, let me see. Maybe, would it be possible? I know that there is a better way to do this, but I'm going to try it because I haven't done it right this second. I know that there might be a way to do this directly and film my screen, but let me try to do this. Okay, so this was with 20. That's not going to be very clear. Let me do it with 200 and 100. Give me a second. Okay, this might be, for the purposes, okay. So I'm going to put it here. Hopefully you can see something. This is a run in MATLAB. It's not the best one, but in the horizontal axis I have 300 tests. 1, 2, 3, 4, 5, etc. Right? That's n over here. So what I'm plotting on the vertical line is this variable, the log of the ratio of the distributions of the probability, and I'm doing that experiment 20 times. And I am assuming, well, not assuming, I simulated a situation where for the first 100 tests there was no damage. Okay? Therefore, this should have been bigger than this, and this tends to go negative. After the 100th, a little bit of damage appeared. So this is a very tough case that I am presenting here, and it's not great for me to get into the details right now, but I just wanted you to see that, hoping that you can follow a little bit. You can see that in all these things, I didn't make them back to 0 or anything. They do tend to drift in general kind of downward, not very fast, because, and then when you get to about 100, which is when the damage is introduced, you can see that there is a trend back to going up, right? So the 100th is the division here between there was no damage and damage has appeared, all right? Of course, if we put a little more damage, I don't know, let's see, not that this is a lot, but let me see. Now you can see with a little bit heavier damage how much cleaner the situation is, right? So the results up to 100 are evident that there is a slight negative trend down, and then after 100 the thing takes off, right? So you're pretty confident by the time you're in like 120 or something like this that damage has taken place, right? In this case, by the way, this data corresponds to 3 frequencies that were 8, 20, and 40, and the damage made them go to 7.5, 19, and 39.7. So the last one hardly changed. And we have something like that. So I will try to conform some practice for you so you can get familiarized a little bit at least with this concept of this likelihood ratio test for change detection. Notice that we talk about change, not damage at a given point, but change, right? All right.